Well, hello there! I hope you're having an amazing day and that you're feeling as excited as I am to have a discussion about our second computer science topic. Today, we will be talking about floating point numbers and their representation in memory and basically how our compiler is working with them. So, let's get right into it. Of course, as usual, we need to start things off by mentioning some prerequisites. If you are here and you did not see the video lesson about floating point numbers, the basics about floating point numbers, that is the previous video I released, I need you to go and watch it from the start till the end. Because if you did not see it, this video is not going to be as beneficial for you as it would be if you were familiar with all the stuff that we covered in the previous video. So, I will attach it to the description of this video, so please find it there and then come back here so we can get this party started. Now that you've seen all the prerequisites and that you have all the basic understanding, it's time to start our discussion about the representation of floating point numbers in memory. The first thing we are going to cover is going to be the basic bit assignment in our floating point numbers. Of course, to make things simpler, we are going to start our discussion with F32 data type, and after we covered all and explained everything, I'm going to extend that knowledge with our F64-bit version. Because basically it's all the same, but just with greater precision and higher ranges. Okay, here we are going to start putting together our 32-bit version of floating point numbers. We are starting things off with the simplest part, and that is going to be the sign. We already mentioned in our previous video that sign for floating point numbers is mandatory, and it basically works exactly the same as for integer numbers. It's that simple, so we do not have to spend more time on this. The second part that makes our floating point numbers is called exponent, and in the 32-bit version scenario, it takes up 8 bits. And finally, we have the third part, which is called mantissa. And this part consists of 24 bits of memory. And now that we got that out of the way, it's time to start discussing and actually learning what those things are and how they work in action. As I already mentioned, I take it that sign is already covered because it's very simple, I already explained it, and yeah, we can continue our journey right to exponent part. So, the first part that we need to address in great detail is going to be dedicated to exponent part of our floating point numbers. So, I'm going to start things off by discussing one part about exponents that is basically not as intuitive as we might like it to be. Let's inspect our exponent part. So, we already said that it's 8 bits long, which means that we have 256 different options that we can put inside of our exponent. And yes, because we want to work with very tiny numbers and have great precision, we need to make sure that we have both negative and positive exponents, and we are going to split them as evenly as possible, and we're going to be able to work with exponents from minus 127 all the way to 128. So if you remember, this is different when compared to the values of integers that we can work with when having 8 bits of memory at our disposal, because there we had from minus 128 all the way to 127. Here it's the opposite. We have from minus 127 to 128, but you will see it in action. And now, do you remember from the previous lesson that we saw in our Visual Studio Code that F32 can represent values starting from minus 3.4 something 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 times 10 to the power of 38. So we have 38 zeros. And here we are talking about exponent of 128. And that makes no sense, right? Well, no. That is because our CPU is not working with decimal number system. It's working with binary system. So if you think about it, the base for the exponent is not going to be 10. It's going to be 2. So basically, we will have 2 to the power of 128 as a maximal value. And if you have enough spare time, you can basically calculate to see what is the value of 2 to the power of 128. And if you do that, you will see that it's basically equivalent to 10 to the power of 38. And that is what we expected. Yes, one more thing about exponents of floating point numbers. You are going to subtract 127 from the actual number that is stored inside of the exponent, and that way you will get the actual exponent that we are working with. Do not worry, we are going to cover it in practice, but I just want you to be aware of this fact. Great! Now that we covered exponents, we can start our discussion about the mantissa. And this part, as I already mentioned in our previous discussion, but shortly, is representing the decimal part of our number and is represented by 24 bits. Aha! I knew it! I knew you've got no clue! You said and showed in presentation that mantissa is 23 bits long, and right now you're all of a sudden telling us that it's 24 bits long. And that does not work, my friend. You've gotta learn first and then start telling us what something is and what something is not. I knew it, it's going to come to this point. So, as I mentioned, we have 23 bits that are being stored in memory, but we also have one bit that is hidden because its value is always going to be 1. It's never going to be 0, it's always going to be 1. No matter what scenario we are talking about, it's going to be 1. That is why we do not have to waste another bit of memory on that bit. And by using those 24 bits of memory, we can represent up to 7 accurate decimal digits in reality. To explain everything, I have to use examples, because like this, it's going to be so difficult for me to explain stuff and to explain it in a good enough fashion so it's really easy to understand that I feel like I would just be wasting your time. So let's work on our example here. Okay, for this example, let's take a number that is not going to be too complicated, but also not too easy, so you would be able to go through all of the necessary steps when converting decimal numbers into floating point number representation. So let's use number -22 times 625 for our example. As you already know, we have a negative number, which means that our most significant bit is going to be 1, because it is dedicated to sign, and we know that it's going to be 1 if we are working with a negative number, which is the truth in our case. The next step that we need to do is to convert number 22 into its binary representation. And to do that, we need to learn how to actually translate decimal numbers into binary representation. So, let's do just that. It's time to learn something new. We are going to cover how you can translate any decimal number into its binary representation. Do not worry, it's not complicated. You will be able to understand it very well after this simple example. And why not learn it while we are translating a number 22? So, what is the procedure here? We are going to divide the number that we have, in our case 22, by 2, and then we are going to be monitoring the remainder of that division. So basically, when we divide 22 by 2, we will get 11, but there is no remainder. It's a clean division, so to say. And when we have done that, we are going to remember that 0. You have to note it, you have to remember it. After that, we are going to our next step. So we have number 11 and we are going to divide it by 2 again. And in this case, it's a different scenario. When we divide 11 by 2, we actually have 5.5. And that means that we do have remainder while dividing. And that means that we are going to remember number 1, because 1 is remainder. So, for example, you can remember it however works for you the best, but it might be the easiest to just subtract 1 from 11, then we get 10. And when we divide 10 by 2, we will get 5, but we also have that remainder of 1. Just write it down again. After this, we are going to divide number 5 by 2, and again, the approach here can be to subtract 1, because it's not divisible by 2. After that, we are going to divide 2 by 2, which is a clean divide, there is no remainder, so we write down 0, and the result of that division is going to be 1. And finally, we divide 1 by 2. Again, this is not divisible, so we are going to remember that 1, subtract it from this, so we get 0 divided by 2, which is 0, and we also had that 1 as a remainder. So we are done. We basically went all the way down and divided numbers all the way until 0, and we got some 1s and 0s as a result of doing that. And now we need to just read those values that we stored, so those 1s and 0s, but to read them from the bottom up. So not from the top to bottom, but from the bottom all the way up. And when we write them down, we will basically get our binary representation of the decimal number we started from. In our case, that's going to be 10110. We can do a quick check on this, just to make sure that we really do get 22 when we convert this binary number into its decimal counterpart. So you know how to do this. We are going to use our powers of number 2. We have 2 to the power of 4. We also have 2 to the power of 2 and 2 to the power of 1. That is basically 16 plus 4 plus 2. When you add that all up, we get 22. Great job! Now you know how to convert decimal numbers into their binary counterparts. When we have calculated the binary version of our number 22, we can hop to our next step, and that is going to be to convert the number that is after the decimal point, so basically 0.625, into its binary counterpart. And in this scenario, the procedure is going to be a bit different, because you're not working with whole numbers as before, we're working with the remainder part of the number. So the procedure is going to be relatively similar to the one that we used for whole numbers, but now we are going to multiply the number by 2 and then check if the result is going to be greater than 1 or less than 1. In the scenario that number is greater than 1, we are going to use that 1 and store it, and then repeat the process. So let's start from the example, let's not theory craft too much. We have 0.625. When we multiply it by 2, we get 1.25, which is greater than 1. So we subtract 1 from that number, and we save that 1 as a remainder, so to say. After that, our next step is going to be to multiply 0.25 by 2, and then we get 0.5, which is less than 1, so we save 0. After that, our next step is going to be to multiply 0.5 with 2, and then we get 1. And when you get 1 as a result, you're basically done. You have basically successfully calculated what is the remainder of the number in binary. In our case, you're going to use 101 as a result. And now we know how to represent our entire number. So we know how to represent 22, and we know how to represent the part after the decimal point, which was 625. And when we put those together, we get 10110.101. Awesome job there! I'm so proud of you. You're progressing so well here. If you understand this, you're doing awesome. If you have any questions about any part of this procedure, please leave your comment below this video. I'll gladly try to explain as much as I can. Great! Now that we calculated our number, it's time to move the decimal point and that way actually calculate what our exponent part should be. Okay, we have our result that we mentioned and we need to move the decimal point and remember how many spaces did we move our decimal point in order to get to the point where we have 1 dot something. Okay, when we move 1 space, we get this result, 2 spaces, 3 spaces, and 4 spaces. So as you can see, we need to move our decimal point 4 spaces to the left in order to get the desired format. So the desired format is what I mentioned, 1 point something. Because if you remember my discussion about Mantissa and that unintuitive stuff that I said that we have 24 bits basically instead of 23, even though we are remembering only 23 bits in our memory, well, this is why we are doing that. Because you are always going to move the decimal point all the way to have 1 point something. And we just need to remember that something part, because 1 is always going to be there. Okay, now we know that we moved our decimal point 4 spaces. So we know that our exponent part should be 4. And if you remember, I told you that we need to subtract 127 from the exponent part to get its real value. So to get what we need to store in our exponent part, we need to add 127 to our number 4 here, which is 131. We need to store 131 in our exponent part of the floating point number. And when we know that, let's jump right into our conversion. You already know how to convert a decimal number into its binary counterpart, so let's jump right into it. We do not have to waste any more time. Okay, we are starting things off from 131. When we divide it by 2, we get 65 and remainder of 1. Then we divide 65 by 2, we get 32 and remainder 1. Then we divide 32, we get 16 and no remainder. We then divide 16 by 2, we get 8 and no remainder again. Then we divide 8, that is 4, and we have no remainder again. Then we divide 4 by 2, we get 2 and no remainder. Then we divide 2 by 2, we get 1 and no remainder. And finally we divide 1 by 2 and we get 0 and 1 as a remainder. And again, if you remember, we are taking numbers from the bottom up, not top to bottom. And when we do that, we are going to get 1 followed by 5 zeros and then 1 1. So this is our representation of decimal number 131. And now basically we have all the parts of our 32-bit floating point representation of number minus 22.625, right? Yeah, that's right. Let's write it down. So we have 1 for the sign because it's a negative number, followed by representation of number 131 for our exponent, which is 1 followed by 5 zeros followed by 1 1. And then finally we have the Mantissa part, which is going to be everything that we calculated without the first one, because that part is always there and we do not have to waste a bit of memory on it. So we are basically going to have 0 1 1 0 1 0 1. And after that, you just fill the rest of the Mantissa part with zeros, because there is nothing to put in there. And that, my friend, was everything about converting decimal number into its floating point representation. I hope that I managed to explain it well enough, because this is not a very simple topic to discuss. It's not a very simple discussion that we had here. So do not worry if something is not crystal clear to you, and please feel free to leave a comment as a question below this video. So we're done, right? Oh no, we are not done. I forgot to talk about F64 version. Well, luckily, things are not going to be too difficult here, because basically everything is going to be exactly the same for the 64 version of our floating point numbers as is the case for the 32-bit version. The only difference is going to be number of bits that are assigned to both exponent and mantissa parts. Basically, the first bit is again going to be dedicated to the sign, and again we use 1 for the negative and 0 for the positive numbers. And then we have 11 bits for our exponent, and after that we have 52 bits for our mantissa. Or 53 if you want to calculate in that additional bit that we do not save in memory, but yeah, basically it's 52 bits are saved in memory. And because of the fact that now we have 52 bits available for mantissa, we can accurately represent up to 16 decimal digits for our numbers. And also, our exponent can get up to 308, because again our exponent part is going to be extended. And basically everything else is exactly the same as for 32-bit version of floating point numbers. You will calculate them exactly the same, you will do all the steps that we covered exactly the same, so there is no need to give you another example here. I hope that you agree. And that would be all, folks, for this video. This was probably the most complex video I released up to this point. Of course, this is just warming up. We're going to cover a whole bunch of very complex topics in future, but up to this point, this one is hands down the most complex topic we covered. And because you're still here, I would like to congratulate you on being such a strong character and managing to get all the way to the end of this video. I hope that you enjoyed it and that you found it useful. And if you did enjoy it, I would like to kindly ask you to subscribe to this channel and like this video, because it would help so much both me and the channel to grow and spread the value to as many people as possible. And for that, I thank you in advance. In our next video, we are going to be talking about the Boolean data type and basic bitwise operations that we have at our disposal. If that sounds like something you are interested in, I would like to invite you to join me on that adventure. So, have an amazing day and goodbye